experienced researchers looking to push the boundaries in thermal conductivity. Sheathed in stainless steel, the TLS, Transient Line Source Needle Method, offers maximum robustness in thermal conductivity testing. TLS is best suited for granular materials, polymer melts, soils, slurries, and gels. C-Therm software provides full data acquisition and analysis in one user interface, allowing full control of all three methods: intuitive, logical, easy. Trident reflects C-Therm's years of experience working exclusively to provide labs, researchers, and manufacturers with the very best in thermal conductivity measurement. C-Therm's products are globally distributed in over 65 countries around the world, with full local support. Trident. It's better to have options.
Hey everyone, welcome to our webinar presentation sponsored by C-Therm Technologies. My name is Adam Harris, CEO for C-Therm Technologies. Very pleased to welcome you to our presentation. This is one of our application-focused webinars, one of the many we hold over the course of a year on specific application areas of interest related to thermal conductivity. Today we're going to be taking a deep dive and looking at thin film materials and how to characterize their performance from a thermal conductivity perspective. The session should last for 30 to 45 minutes. We will reserve some time at the end of the session for a question and answer period. But as we go through the material, if you have any questions or comments, please feel free to take use of the chat box. A great way to register any thoughts or ideas, or maybe some aspects you'd like us to maybe delve a little bit deeper into. Certainly, please feel free to make use of that. But first and foremost, thank you for joining us today. We'll be looking at some of the different methods available to characterize thin films, and we'll talk about some of the different aspects of testing them. I'm the warm-up act. I'll be introducing my colleague here, application scientist Arya Hakimian, here shortly. He's a specialist in thermal conductivity methods, brings a tremendous amount of expertise on method selection and an understanding of how the different techniques work. So he'll be walking us through a curated session on testing thin films. But just before I introduce Arya, I wanted to provide a little bit of background on who C-Therm Technologies is, talk a little bit about some of the technologies that will be highlighted in today's presentation. I see some of our customers on the line with us today. A shout out to Matt and Edward. Great to have you online with us. And I see many faces that are maybe new to C-Therm and aren't quite as familiar with who we are as an organization. So let me just provide a little bit of background. We're a Canadian tech company that really specializes in the area of thermal conductivity testing. Our raison d'etre, our reason for being in life, is all about simplifying thermal conductivity testing largely for the materials of tomorrow. So the new composites, the new formulations that are being developed, whether that's to help better manage the thermal heat in an electric battery pack in an EV, or maybe it's the design of some of the latest thermal interface materials in a smartphone. These are the types of scenarios that we support day in, day out, helping our customers better access that performance data, simplifying the process for measuring it, and really empowering these measurements to be done under more representative conditions. Because when we talk about thermal conductivity, it's really important to understand how the environmental factors play a role in the effective thermal conductivity performance of the material. Different compressive loads, humidity, temperature, all of these things can influence the effective conductivity of material. So we focus on the development of transient methods, which are fast. They offer the flexibility to test a lot of different geometries and shapes. And they also give you this power to test under more representative conditions, some of which we'll highlight in today's presentation. Now, we launched a new product on the market about 3 years ago called Trident. It's been a tremendous success for us. It's doubled our top line sales over that period. And the reason it's been so successful is because Trident recognizes, first and foremost, fundamentally, that when it comes to thermal conductivity, it's important to have options in the method selection. A lot of the bad data out there in thermal conductivity is from taking a good method and applying it on the wrong type of sample. Right. So in thermal conductivity, you really need to have some options, because there's no universal solution that can test all of the different types of materials. For example, we're talking today about thin films, which are a unique type of material to test. But you can also think of testing conductive materials, insulative materials, anisotropic materials or isotropic materials, different material states, liquid, solid, phase change materials. These all have their nuance and have an impact on the method selection that's most appropriate to determine an accurate, effective thermal conductivity for the material. So with Trident, we bring together the three most prominent methods for thermal conductivity testing. We have the MTPS method, which is the one on the lower right of the Trident pyramid-shaped box. This is fast, easy, very good precision statement. Can test solid, liquids, powders, paste. It's probably the most popular of our sensors, I would say. The one in the middle, we won't be talking a lot today about, but is very useful in polymer melts. In other applications that get quite sticky, or you're worried about bonding the material, that stainless steel needle probe is sheathed in stainless steel, so it's a very robust sensor and great for some of those situations. And then The last one, which you will see pop up quite a bit in today's presentation, is the Flex TPS. That's the yellowish sensor. That's a sensor that sandwiches in between two samples. It's a nickel foil that's encapsulated in a polyamide. We call it the Flex TPS because it's a flexible sensor, but it also gives the user the flexibility over the timing power parameters. There's different size diameter sensors available for the Flex range of sensors. So really giving you more influence over the measurement and its regression. Conversely, if we compare it to MTPS, MTPS is really point and click, very simple to operate. So when you look at that capability all in one instrument, this is where Trident really shines. And the tagline here is it's better to have options. And that's so true when it comes to thermal conductivity. When all you have is a hammer in life, everything looks like a nail, and you apply that blunt instrument in all situations, it's not always the optimal tool selected. And so with Trident, this gets to the heart of the value proposition, which is really having the best tool at hand for the given situation. Now, because there's a variety of methods available, it's helpful to have guidance on method selection. And this is something that ARIA is really good at. You'll get a sense of that in the presentation, but there is some additional resource materials available, freely downloadable. There'll be a link provided. I see Angad's dropping it in there now. Thank you, Angad. This is a free resource. I think it's about 50 pages of content. It describes the different methods, steady state and transient methods, where they're applicable, where they're not, what are their principles of operation, what are their limitations. Very, very helpful in selecting the methods so that you can set your measurement and data set up for success. Just as I transition this to ARIA, sometimes, I mentioned we have a few of our clients on the call today. Very grateful to have them back online with us. This is a quote from one of our clients at Intel, Hardeep Singh, a senior thermal engineer at Intel, just commenting on the value of Trident. Allows us not to only test a relatively broad range of materials with various sensor techniques, but with the slab utility, we were able to easily test the thermal conductivity of our thin aluminum alloys, which have a high value in today's electronic and computing hardware. Just a nice expression of a typical client experience with C-Therm. And there is a link, I think, coming in here that if you want to look at other customer references, certainly free to do so if you want to pick something that's maybe more representative of your application space. Now, I will put a short plug in here for Rigaku. We are the representatives for Rigaku in the US. Rigaku is a very impressive Japanese company that has done some really novel, interesting things with thermal analysis and calorimetry. So one of my favorites is their DSC Vesta that has sample observation included with it. So you can actually visually monitor the sample as it's going through a heating or cooling cycle. This can be very helpful in really understanding how a novel material is performing. Sometimes in a DSC or calorimeter run, you'll see a very low energy event or low signal event happen, and it's sometimes a question of, well, what is that? Is that a real thing? Is something happening to the sample there? Being able to visually observe a color change, a decomposition, a combustion of the material, super interesting, and ultimately helps you tell the story of your materials better, whether that's internally to your development team, to your product team, or to your customers and partners externally. Seeing is believing, and being able to really observe that sample, I think is it's a great feature. We're going to feature some of the data, I think, in this presentation from Rigaku, so I will just put that plug in there for the Rigaku thermal analysis product line. All right, at this stage, I want to invite my colleague Arya online. There he is. Arya, great to have you with us again. I understand you've put together a presentation on testing thin films. You're going to be highlighting some different published works and some work generated internally. So I'll get out of the way here and introduce the star of the show, Arya Hakimian, application specialist here with C-Therm Technologies. I'll rejoin you all for the Q&A session at the end. Thank you.
Awesome. Thank you, Adam. Hey everyone. As was mentioned there, I'll be going through a little bit of a presentation here covering thermal conductivity testing of thin films. Um, all that said, we'll jump right into it. A lot of the times, and I'd say especially in recent years, the main application for a lot of these technologies are revolving around thermal management, being integrated into different electronic components, whether that's in things like the picture on screen of a cell phone portable device, or and especially in recent developments with EVs and XEV systems, integration into those different platforms. Now, all this is to say, of course, temperature is a large potential, it's a large area with varying factors that account for a large majority of these different types of failures. Noting here about 42% from this 2017 conference. The idea here is that these materials being incorporated into some of these very small form factor systems are there to help alleviate some of that thermal stress that is generated. Now, how is this done, and what's really an important aspect to these materials is related primarily, we'll kind of note this to the thermal conductivity. So the thermal conductivity, if it's a new topic for you, if you're unfamiliar, this really describes a material's ability to conduct heat. It's an intrinsic material property, and what that means is irrelevant of the size or the shape of the sample. It is something that will be true to that material in and of itself. For us here today, focusing on thermal conductivity and standard SI units, all data will really be presented here in terms of watts per meter Kelvin. Now, as Adam mentioned, there's a range of different test methods out there for thermal conductivity characterization. Again, I won't be spending too much time on this, but I did just want to give a little bit of background information on some of the different methods that are out there and how they are applied, kind of what types of materials they're really geared towards. At a very high level, we can break out the methods into two, I'd say, large categories: steady state and transient. So as we can see from the list, steady state includes your methods like heat flow meters, guarded hot plates. We'll kind of have a little bit of discussion on those, but of course, we're really focusing in on here today are transient methods, and specifically contact-based methods, transient techniques. So the transient plane source, modified transient plane source, and transient line source. Many may have experience with laser flash as well as kind of a measurement technique. And while this does fall under the transient class, of course, it is done with non-contact based on the laser, the light source that is used for the technique. So just to kind of go over these again, very high level, your steady state methods, generally speaking, these are really applied towards lower conductivity insulation-based samples. They operate based on the heat flux measurement. So you kind of see in the example setup, you'll have your sample in between a hot and a cold plate, and you'll set that up under a specific test profile to establish the heat flow through the specimen. Now, these, again, great for kind of those low conductivity installations, but not really as good of a fit when you're dealing with high K samples or materials that have anisotropic behavior. The other thing just to be aware of is these results that you're getting from these measurements are really, an average you can view it as across a very large surface. Typically, these samples are quite big. Large coupons are cut out and placed in between these plates. And what you lose in that is the ability to detect small spot-to-spot variation or even side-to-side differences, which can become an issue, especially when we're dealing with these thinner materials and these thermal management systems. So just something to keep in mind. The other thing with steady state, I'd say the biggest drawback is while they are very good at what they do, they generally carry quite long test times. So, you're talking minutes to hours, depending on the type of profile that you're setting up and running. However, they do conform to some very well-known standards, such as ASTM C177, ASTM C518, and so forth. I will also just kind of mention a little bit on laser flash because, again, while this is a transient-based measurement, there are certain limitations that you'll need to be aware of. Ultimately, if you're dealing with very high temperature testing, kind of referring to this anything really above 500 degrees Celsius, laser flash is going to be the best option. It's a very powerful tool for those high temperature test requirements. But of course, there are certain limitations. It's a really good fit for those homogeneous solids. Again, a lot of people apply this for testing of ceramics, metals, but there are certain issues that can be present if you're testing composite materials, those that may have anisotropic behavior as well. There are some sample requirements here based on the sample coupon needing to be placed inside of a specific holder. There's like a little sample holder in these types of systems. But again, it's a good, valuable tool and also conforms to the ASTM standard E1461. Now, again, that's really not the focus of what we're looking at here today. We're focusing in primarily on these transient-based measurements that are available on the Trident platform. Adam gave a bit of an introduction there at the beginning, so I won't go over this again here, other than to say the ability to really pivot to the desired method of interest can be quite advantageous depending on, again, the sample type and the sample format that you're working with. So why do we focus on transient? Really, I'd say number one is it allows us to apply representative testing conditions. These sensors are very versatile in the sense that they can be applied in different controlled environments, different atmospheres, under different temperature, pressure conditions. They lend themselves very well to these types of setups. And of course, if you really want to understand how your material is going to perform under a certain set of conditions, mimicking those conditions for the actual testing is going to be of great importance. The other thing, and of course, what many groups are, why they will gravitate towards these types of techniques is they're much faster than your traditional steady state options. Inherent to how steady state techniques work, that heat that's entered into the system, those systems need to enter into steady state related to the name. Transient are always going to be faster, just based on the fact that as this temperature is changing within the sample, changing dynamically over time before it even approaches that steady state condition, we're able to take the measurements from there. So inherently, they will always be a faster option. And again, the final note here, just greater flexibility on sample size and also sample format. So testing solids, liquids, powders, pastes, amongst others. There you have a lot of flexibility on the type of material that can be tested at and in what phase it is present. So we're going to be starting out with a little bit of discussion focusing on the flex transient plane source, or TPS for short. A little bit of background, again, if you're unfamiliar, the TPS method, it's a double-sided sensor. It also provides measurement for thermal diffusivity. So thermal conductivity and thermal diffusivity are provided in the measurement using this technique. We call it flex, kind of related to the fact that it offers the greatest flexibility over your experimental parameters. So the time and the power are the two main things that are adjusted and set for a TPS measurement. And you as the user have full control over this. There's no contact agent required. That is a nice aspect depending on certain sample formats or materials that you may be working with. But really where TPS shines, and I'll go into this in a little bit more detail in a few minutes, but it's with respect to the specialty utilities that are available. So slab anisotropy, and of course the focus for today, thin films, it opens up some unique testing capabilities that we'll discuss. The TPS, I will flag just at a high level, is a little bit more complex from an operational standpoint. So we do really recommend it for more advanced users. But of course, if it is something that is of interest, the training we can provide on this will of course get you set up and running and comfortable with using the instrument. Last note, it does conform to the ISO standard 22007-2. something to potentially take a look at if this is a method of interest to you. So I'll give a very brief run through on the principles of operation here. With the TPS, some things to be aware of. I mentioned it's a double-sided sensor. So from a setup perspective, you will need to have two samples in contact if you're running in kind of your standard mode of operation. So one sample goes on top and one goes on the bottom side to create this stack. As I mentioned, the test parameters, these are things that you have control over and can adjust depending on kind of the method that, or I should say the utility that is used and type of sample. These need to be adjusted accordingly, but mainly the time and the power are the two that you'll need to focus on. You also have access to some different sensor sizes. So with respect to being flexible on sample size, the sensor will ultimately dictate the size of the sample that is needed. So there are 3 different size options that we have available on the Trident platform for the TPS method. Now, at the end of the day, once you get everything set up and you run your test, you have your parameters set, you run your test. The data that we're collecting for these transient techniques will be quite similar across the board in that we're monitoring that delta T, that change in temp that occurs as a function of time. But the reason I mentioned that this is a little bit more, I'd say, geared towards some advanced users is related to the fact that after the test is complete, there is a verification process that you have to run through, basically validating the settings that you've used and the results that were obtained on the material you're testing. Because you can imagine the time and power settings, you can somewhat arbitrarily adjust those to whatever you want to. Doing so doesn't necessarily guarantee that the results that you get are going to be valid. So there's this verification process. It stems from guidance that's provided in the ISO standard. But essentially, there's about 6 or 7 of these checks that you need to run through in a standard measurement. Some of these are quite quantitative in nature, so certain criteria just simply have to be met through a calculation that is run. Others are more qualitative. Certain trends in the data, certain properties of the results that are generated need to be investigated. But ultimately, at the end of the day, there is you can call it a roadmap that's set out for you that we, of course, provide training on. And again, you'll be able to follow this through and verify your test data, make sure it is, in fact, correct. Now, before I talk about thin films, I do just want to give a little bit of I'd say the intro to the entry-level mode of testing, which is your TPS bulk utility. So if you did ever need to test kind of more macroscopic, like bulk size materials, TPS is a really good option there. The bulk utility is geared towards these isotropic materials mainly, so just to flag that. The size of the sample that you need for the bulk mode of operation will scale based on the sensor size, as I mentioned. So you can see there's a 6, 13, and 30 millimeter size option. The diameter of your test sample needs to scale 2.5x the diameter of the sensor, and the thickness of your test sample will scale 1x the size of the sensor's diameter. And again, keep in mind that where this is a double-sided method, you will need 2 samples produced, one on top and one on the bottom, to perform the measurement. Now, again, the reason why the TPS is of great interest in many groups is towards some of these more advanced utilities. And for us here today, the one that I'm primarily focused on is the thin films. This is, of course, the topic of our discussion here today. So I'll give a little background on how this method works and some kind of example data that you can collect. So for the TPS thin films utility, a few criteria, things that need to be understood. It's really geared towards polymeric materials. Generally, getting below 5 watts per meter Kelvin is where you'd want to fall. The measurement that the TPS thin films utility provides is a through plane measurement. So I know there is a lot of interest in establishing in and through plane thermal conductivity data for a range of materials that are used in today's products. Just to flag that the TPS does provide you with a through plane measurement. So when we're talking about sample size here, with respect to the thickness, we can go down as low as about 10 microns. So whether your sample's 10, 100, 200 microns thick, these are things that can be tested with this utility. These films do need to have a fairly good control over the thickness uniformity within the film itself. Thickness is a component of input in the software for this type of measurement. So ensuring a good quality measurement of that thickness and uniformity within the sample is going to be very important to get the best quality results. And essentially for the thin films utility, the procedure for the test involves this successive layering procedure, as we can kind of see example or demonstrated on the right-hand side here. This setup will involve a few things. First, you will need a conductive backing material. This will essentially surround the top and bottom side of the sensor, and then when you add in the sample as well. This backing material, again, what this is essentially doing, and I'll go into this a little bit in further detail, but we have a material of high conductivity acting essentially as a blank in kind of your initial measurement. And then subsequent measurements from there will be introducing a layer of film, and you may repeat this a few times. But the idea here is that we're going to have some sample that's conductive and typically at least an order or two of magnitude higher in conductivity than the film itself. So how this works is essentially as you start with these measurement points, starting with your blank and then adding in your film, what we're doing is we're subjecting the material to a heat pulse over a defined time period. As you incorporate the layers of film, what you'll see is a shift in that temperature profile. We can correlate that temperature shift to a temperature related to the thickness of the film at that point. And the idea here is you're building out these points. You're taking multiple measurements to effectively regress a straight line through to get at the thermal conductivity of the material. This is all handled automatically by the software package, but the procedure involved is essentially this discrete measurement at these different layers. What the Trident software will kind of look like, I took a screen grab of a test that was run a little while ago, but just to kind of show you what that can look like here, you can see that you're getting these individual points measured at different thickness levels of the incorporated film, and then that line that's generated, the conductivity and all this data is automatically provided to you within the software package. So it makes it quite easy from that side of things. Thermal conductivity of a range of these film-based materials have been, characterized internally, and this is, kind of an example data set that you could be obtaining with this type of measurement, noting a few different kind of, I'd say, common film materials compared to the literature value. We're seeing really good agreement, generally here within about 5% of the reference results. Now, I mentioned that testing of thin films can, of course, be, with this method, limited to mostly polymeric films, but if you were interested in testing high conductivity films, and these are really referring to metallic-based films, the TPS thin films utility may not be the best fit there. However, I do want to provide you with a potential route on how to deal with these materials as they can be more challenging. And this is related to the slab utility. And I'll kind of go through this, but the idea with the slab utility, and this is a little excerpt I took directly from the ISO standard. It states that you can apply this for samples between 1 and 10 millimeters thick. The setup example that we see in the bottom here is essentially the opposite of what I was talking about with thin films. You have, in this instance, an insulative backing material surrounding your test sample and the sensor, so it's kind of opposite in its approach there. However, one of the things just to kind of be aware of is we have done testing on, I would say, much thinner samples below the spec ISO range here of 1 millimeter. This image here is of an aluminum foil sample that was tested in-house. And the data that we've collected is really well in line with what was expected. So I just want to kind of use this as a quick example. An aluminum foil, this was about 130 microns thick, very kind of clearly highlighting that this is technically outside of the standard ISO test range. However, the results compared to the reference values were extremely close. We're within 1% of the reference value provided on these samples. So of course, applying these methods to something that is a little bit outside of the kind of scoped range can be challenging, and if it and doesn't guarantee in all instances. But for these well-defined sheets, and I call them more so foils, aluminum, certain copper foils, things like this would be something that could potentially be an avenue to test these samples if you are stuck kind of trying to find a method to accommodate that test. Now, I do also, just while we're kind of in this discussion, want to talk about the modified transient plane source a little bit as well. The MTPS, of course, is a single-sided test method. It's quite different in its design. It measures thermal effusivity of the material as well. This, I will say, the MTPS is much easier to operate. It's a much more simplistic testing approach for thermal conductivity. It's also much faster. It is the fastest of all the methods that we provide on the Trident platform. Measurement results are taken in about 1 to 3 seconds. So just understanding the speed there. And it is also, I would say, the most versatile. So if films are your only sort or material of interest, then potentially some options there. But if in your lab that has multiple different kind of projects going on, different samples, the MTPS is really going to be the most flexible there with the type of material that you can apply to it. So from a principles of operation standpoint, kind of again, just to go through this kind of from the top down, the coil on the MTPS, we see here there's a spiral heating element. This is on the top side of that sensor. This is what's used to deliver the thermal pulse for your measurement here. Somewhat similar in all these transient-based techniques is that as that heat is being delivered, the sensor is simultaneously monitoring. You can view that as the change in temperature or the change in voltage across the sensor as a function of time. Excuse me. Now with the MTPS, the material that's in contact, and of course what you'd see in the output is the response will be different for whether you're testing something more insulative or conductive in nature, but the overall rate of change that is observed in that very short defined time window is what's used to determine the thermal properties of the material. With the MTPS, there is no manual component of data analysis required. It is fully optimized from a factory level. It operates off of preset calibration settings. So you as a user would simply need to set up the calibration you want to run with, and this will take care of all of the settings, all the test parameters for the measurement itself, the data analysis, and all of this. So we do describe it as much more of a plug and play solution, which of course can be appealing depending on the environment in which the testing is being done in. The other thing with the MTPS I will just flag is referring to the guard ring. You can kind of see that picture there in the top left image. The guard ring surrounds the active zone of the sensor. What this effectively does, it supports a one-dimensional heat transfer into your test sample. What this really means for you as a user is that with the MTPS, you will be getting a directionally dependent measurement with that heat pulse traveling normal from the sensor surface. And I do want to just flag some of this. This was some data that was collected by our distribution partners, Rigaku. Adam mentioned earlier, they offer a line of calorimetry instruments, but they are also our distributors in Japan. And this is some data that one of our colleagues over there generated with the MTPS on these films. Now, for testing of a film on the MTPS, just to be clear, the MTPS will have a limit, a minimum thickness requirement. And when we're talking about polymers, typically around 1 to 2 millimeters or so. This is something that will vary depending on the properties of the material. So something like a polymer compared to a metal will have two very different thickness requirements. However, what we have some groups doing, and what is detailed really nicely here in these results, is the ability to stack up the sample to do a couple things. One, to establish the minimum thickness limit, so in the Z direction, or that through plane thickness, to be able to get a conductivity measurement of that material. You can stack up those individual layers and clamp them or compress them together in some form or the other. This will not work for extremely high conductivity materials or samples that have very ununiform or non-uniform surface qualities. You'll get, of course, increased contact resistance issues in between those layers. But for something that is very smooth and well-defined, like they were testing here, it's a great option. And the other thing is what you can do, if you have enough of these layers stacked up and you are able to rotate those samples around, as we can see the different orientations that were tested, based on the positioning of the sample on top of the sensor, you can control the direction of your measurement. So that heat pulse is always, you can imagine, traveling up from the sensor into that test sample, and I kind of view that as a straight line going up. So if you rotate the sample itself, you're changing the direction of what's being measured in that material. And in this example here, what they were showing is some very typical behavior of a kind of a standard anisotropic material, where the through thickness direction of their material was coming in lower compared to something that was rotated and measured through the X and Y direction. And we can see almost identical results there coming in the in plane. So indicating that whether it was the kind of the Z, or sorry, the X or the Y, that in plane value is consistent, but both of those being different from the through plane. So just some work I would like to highlight from our partners there. The other aspect to the MTPS, and in this example, this is shown on more of a kind of a bulk sample. This was a molded an epoxy with a conductive metal filler dispersed within the matrix. But this can be applied to really any sample type, whether it's a film that has these fillers during the production, larger samples that have fillers, things that have coatings, or just simply structural defects that may be within the bulk of the material that you're not able to visibly detect. The ability to map at these different spots or different locations across the surface is really a valuable aspect to the MTPS being a single-sided technique. So what you're going to see as kind of shown in this example here, by placing the sensor at different locations, we can get these really quick measurements, and then of course correlate that to things that may be going on within the bulk of the material. For the example here, we're linking this to the filler concentration. So if you look at spot number 2, kind of towards that top left of the central image, there isn't very much filler present in that zone. If you look to the left, to the image on the right, the top left, that result coming in at about 0.347 watts per meter Kelvin, essentially one of the lowest values that was reported during this testing. Now compare that to, let's say, spot number 3 in that central image, so just to the right, much more densely populated with that conductive filler. And as we can see, the correlating result on the right image is almost 3 times higher, coming in about 0.968. So with this, it kind of just shows how the MTPS can be applied across different areas of a sample, and you can get those individual location measurements. And in this example, as you can see, very non-uniform results are present across the sample itself. This is some of that data that you may be missing out on if you're applying a method like something more along a heat flow meter or a laser flash system. You wouldn't be able to pick up on these types of potential issues that could be present. They either get averaged out or just simply disappear within the measurement that is taken, and you can't pick up on them. So again, in this example, kind of a very obvious one, you could just look at this material and tell it's not a great, this was coming off your production line, that you wouldn't be too happy about it. But for materials that may be more opaque in nature, or you're not able to visibly pick up and detect those issues, the MTPS can be a very powerful tool for that type of screening. And lastly, I'll just close out with a paper that I found. This was one referencing the MTPS for testing polypyrrole nanotube films for flexible thermoelectric applications. This is some work that is coming out I believe some joint work coming out of Singapore and China. So, just to kind of briefly go through the study, and this is really just to highlight some of the potential capabilities or things that you might be able to do with the system as it might relate to your work. Kind of as an overview, they produced two different freestanding PPY films. These are formed from various nanotubes being deposited in a manner that they form these sheets or these films. They use two different methods, and not going too deep into the chemistry here, but essentially two different versions of the film from the same kind of precursor material were investigated. And thermal conductivity of the films were measured using the MTPS methods. Again, looking at that through thickness property in this case here, because they didn't do any stacking of the film. But samples were tested from about ambient to 100 degrees Celsius. So they were interested in, I'd say more so the influence of temperature on the overall resulting properties of these materials. Here we can just simply see some results and kind of the trend that was observed across the different temperature ranges for these two samples. We can see the PPY2 film was consistently higher in thermal conductivity, although both of them had a very similar net trend in increasing conductivity as a function of temperature. Now, if we kind of take a look I read through the paper, they were basically linking the fact that the nanostructures of the films, again, because they were produced in two different manners, were a little bit different. The one on the bottom there, the PPY2 film, had a structure that was lending itself to a significantly improved heat transfer, or should I say slightly improved heat transfer compared to the prior. So they were relating the fact that the overall structural performance was linked to the thermal conductivity results that they were showing. But yeah, so that brings me essentially to the end of the presentation here. Just some concluding remarks. Of course, these thin films or films can be quite challenging depending on the type of method that you're looking to apply to it, especially looking at some of those more traditional measurement options. The Flex TPS, it does offer that unique testing capability to measure these thin films directly down as low as about 10 microns in thickness. But also on the other side, the MTPS, so C-Therm's proprietary sensor design, it does provide you with some setup options to measure these films if they were kind of more described as, in the kind of millimeter range or thinner via stacking. The other nice advantage with the MTPS, of course, as was highlighted, was the ability to kind of do the directional dependency by rotating those samples around, and of course the thermal mapping as well. So that being said, just again, like to reiterate, thank you everyone for kind of your attendance here today. I do believe we'll have a little bit of some outro kind of wrap up here. I'll invite Adam back on to kind of discuss that. But if you did have any questions, I know there were some in the chat box that we'll get to here a little bit later. Happy to kind of reach out one-on-one. If you did have any questions, my email is on screen. Feel free to reach out, or on LinkedIn. Happy to continue these conversations offline. Thank you very much.
Thanks, Ari. Great job as always. I'll just bring up a few slides here on the outro. Yeah, so I think as Ari referenced at different points in his presentation, on our website, there's a great wealth of technical resource material. All these webinars are recorded and available for playback in archive format. If what you heard today was really interesting and you can think of a colleague that might benefit from it, please feel free to share it. It's free content, free to share. There's also a searchable database of all the application notes, including some of the ones that were highlighted today, which can be very helpful in just kind of mapping different application areas to these characterization methods. If you're looking for us at some upcoming events, we'll be at the Thermal Management Show for EVs, HEVs, later this month in Munich. My colleague Anna will be there. Please feel free to reach out if you're going to be in attendance and would like to discuss aspects of material characterization. Our next webinar is scheduled for later this month on testing geological applications, so looking at different material characterization of rock, sand, soil, etc., including some work with pressure in this field. That should be a great topic for anyone that's interested in the geological characterization of materials. One of the things I love about this field is there's such a diverse range of applications. Sometimes it's testing dirt and soil and rock. Other days it's conductive films and textiles and all kinds of interesting things. So really nice diversity. If you're looking to stay in touch with us, maybe you're just kind of getting a feel for some of the different capabilities out there and just want to keep apprised of developments in this space. We're very good at keeping our LinkedIn page updated. I encourage you to follow us there. Any new papers that come out, any new events we're attending, typically this is the central point where we share that information. So certainly a good way to stay in touch. Now, if having reviewed this so far, you're thinking, gee, this is pretty interesting. I wonder if it would work well for my materials, or I'd like to learn a little bit more about maybe how that testing sequence runs with thin films or some of these other application spaces. Best thing to do would be to hop on a virtual demo session with us. We have a library of materials that we can pull from that represent a broad range of applications. So if you'd just like to get a sense of what it looks like with your own eyes and seeing it real time, there's a great option to do that. And I think Angad has dropped in that, that link for booking a demo. So would love to have some folks join us for a demo. With that said, we're going to conclude here the formal part of the presentation. Thank you again for taking an hour out of your busy week to join us online and talk about this stuff. We love having this opportunity to connect with you as an audience. And the one thing we love more than that is when we can get the conversation going both ways. And so that's what we're going to progress to next with the Q&A session. I see there's several good questions that have come in over the course of the presentation. So we will stop the recording here and pivot to the Q&A session. But if you're dropping off, I wish you a great afternoon or evening wherever you are in the world. And we'd certainly love to stay in touch and maybe pick up the conversation one-on-one in the future. So thank you again. Great job, Arya. Thank you to Angad and John for helping organize today's event. A wonderful job as always. Okay, folks, have a great day. We'll move to the Q&A.